Okay, so let's calculate the molar concentration of hydrogen and the pH of a solution, but this time of a weak acid. So the problem reads the concentration of a sample of vinegar was found to be 0.75 molar of acetic acid. Chemical formula, calculate the values of the molar concentration of hydrogen ions and the pH of the sample. Nothing new here. We're going to set up our ice table and we're going to go ahead and start filling it out, okay? So initial concentrations for the acetic acid, we already have that. It's right here. All right, so that's going to be 0.75 molar. Okay, the initial concentration of the hydrogen and the acetate ion is going to be 0. Okay, then we're going to go ahead and go through the changes. So the change here is going to be minus x because it's a 1 mole, right? This is going to be plus x, and this is going to be plus x. All right. Now, when we do the change here, we're going to go, this is going to be 0.75 minus x, and this is going to be x, and this is going to be x. All right. We already know that the Ka for this solution is going to be H plus times the acetate ion. All right. Over the HA, which is the concentration of the acid, which is H. Okay, so here we have our Ka. Now, keep in mind that right here, we're going to take a look at our equilibrium concentration of our acetic acid. In this case, we can go ahead and neglect this value, yeah? Now, I'm going to show you an instance where that won't work, but for right now, we're going to go ahead and go through with it, and I'll show you exactly what I mean in just a minute. Okay, so now that we have our mass action equation set up for our Ka, right, then we can go ahead and calculate this. Ka is equal to x squared over 0.75. Okay, now the Ka for this acid isn't given in the question, but there is a reference chart that we look up, and it actually gives us the value of the Ka for acetic acid, and that value is 1.8 times 10 to the negative 5. Now, of course, you're not going to have a chart on the exam, but if you need to know the Ka to calculate a molar concentration, then you will be provided with the Ka value over 0.75. Okay, so now we have it set up. Okay, so what we're going to do now is we're going to go ahead and we're going to solve for x. Scoot up a little bit here. Okay, so let's go ahead and get this set up. So right now, here's what we have. All right, I'm going to bring this guy over here, and I'm going to be left with x squared is equal to 1.8 times 10 to the negative 5. Okay, I'm going to multiply that by 0.75. Okay, and then I'm going to simplify this a little bit further. I multiply these two, and I end up with x squared is equal to 1.35 times 10 to the negative 5. Okay, now to get the value of x, I take the square root of each one, and I find that x is equal to 3.7 times 10 to the negative 3. All right. Okay. Since we know that x is equal to the value of this here, right? Here's what this means, right? That means that our molar concentration of hydrogen is equal to 3.7 times 10 to the negative 3 moles per liter. Okay, this is our molar concentration. Another way to write this is that it is 0.0 or 0.0037 moles per liter of our molar concentration of hydrogen ions. Okay, now remember that the pH is equal to the negative log of the molar concentration of the hydrogen ion, right? So what that means is if I take the negative log of 3.7 times 10 to the negative 3, okay, moles per liter, then I'm going to end up with a pH value of 2.43. Okay. Okay. So a couple things we're going to take a look at here, okay? All right. Let's take a look at the original molar concentration of the acid, which was 0.0. So 0.75 molar, right? That was our initial concentration of the acetic acid. Now, let's take a look at our calculated X, right? So in this case, it's 0.0037. Okay. Now, what we see here, right, is the value of the calculated X, right? Let me see here. Is in fact 1/10 smaller, because if you were to take a look at the concentration of the starting concentration of the acid, right, it's here, 0.075. Now, the change in the value of X is here. So if your calculated X is smaller by more than 1/10, for example, right, in this equation, then you can neglect this, right? That's when you can neglect the X there. Now, if this calculated X ends up within this amount of significant figures, either here or here, where it has an effect on this number directly, then you don't neglect it, right? That's how you can tell for sure. If that's the case, then you would have to go back and solve this problem using the quadratic equation, because you're going to end up with a trinomial, right? So that's how you can tell for sure whether or not you would need to go back and recalculate to use the quadratic equation. Now on the exam, you're not going to be asked to do that because you're under time constraint, right? So most of the time, it's fair to assume that you're going to be able to neglect this value here. So if that's the case, like, I wouldn't stress too much about it, but just keep that in mind, okay? That's when, because I know you guys had asked me that question. Okay, now, what does the Ka represent? So let's take a look. We calculated the Ka, right? Here's what we want to take away from this Ka. If the Ka, right, is greater or less than, 10 to the negative 3, right? Then you can be sure that this is going to be a weak acid. If the Ka is about 1 to 10 to the negative 3 in range, then that is a moderate acid. Okay, and if your Ka is greater than 1, then you have a strong acid. Okay, so if you're given a Ka for a particular acid, and the question is asking something along the lines of, well, is this considered a weak or a strong acid? You simply have to look at their Ka values, and that'll give you a quick, just a quick reference to determine whether or not it's a weak or a strong acid. Now, here the Ka for acetic acid is here. So you can clearly see that this is much smaller than 10 to the negative 3. So yes, acetic acid is considered a weak acid, and you can tell by this rule here. Okay? All right, let's take a look at another problem. Okay, so here we have calculating percentage ionization of a weak acid. We're going to use the same acid just to kind of keep things simple. We're going to change the initial concentration, and this is going to be pretty much the same reaction. So let's go ahead and let's set up our ice, which we did already, and let's go through this problem, okay? All right, so the initial concentration here is what we see is 0.10 molar concentration for the acetic acid. Okay, again, the initial concentrations here are 0. The change is going to be minus X. Okay, remember the X is the amount ionized. So this is the amount that's going to be ionized, right? How do I know that? I know that because the X is going to represent this guy's here. So the amount that the X represents is how much of that hydrogen ion was released into solution. Now, in this case, this is also going to be a plus X. This is going to be a plus X because, of course, they're all 1-to-1 ratio. And then we're going to go ahead and combine everything. 0.10 minus X, and then this is going to be X and X. Remember again that the Ka is the same thing. All right, this is H plus, this is CH O2 over okay. All right, so again, in this situation, right, we're going to go ahead and neglect that X. Okay, and we're going to go ahead and set this up. All right. Now, again, we already know the Ka for acetic acid. It's the same value, so let's go ahead and get this going. It's going to be 1.8 times 10 to the negative 5. That's going to equal X times X. All that is going to be over 10, right? Because we're going to go ahead and neglect that X one more time. Let's simplify this. That's going to be X squared over 0.10. And that's going to be equal again to 1.8 times 10 to the negative 5. Okay. All right. So let's go through the process. We're going to skip a couple of steps here because it's the same thing. We're basically solving for X. So let's get to the point where we figure out that X is going to be equal to 1.3 times 10 to the negative 3. Okay. 1.3 times 10 to the negative 3. And let's take a look here. Okay. Now, what we're saying here, right, because X represents the molar concentration of hydrogen. So again, the concentration of hydrogen ions in the solution is equal to 1.3 times 10 to the negative 3 moles per liter. So this is how much hydrogen has ionized, right, in this solution. So to calculate the amount of or the percentage ionization, we have a formula, okay? So percent ionization is equal to the amount of HA ionized, all right, divided by the amount of HA available. Okay, and then we're going to multiply that value by 100. Okay, now we just determined that the amount of free hydrogen ions in solution was 1.3 times 10 to the negative 3 moles per liter. But we had an availability of 0.10 moles per liter, right? From our initial concentration. That's how much acid we had in the solution. And of all that acid, this amount was the amount that was ionized. So if I take these two values, I divide them and multiply them by 100, then what I end up getting is that we get about 1.3% ionization. So ionized, right? So because such a small amount, right, such a small amount of hydrogen was released into solution, going back to our definition of an acid strength, the more ionized or more complete the ionization or dissociation of the hydrogen is regarded as a strong acid. Now, we've already established with the Ka that acetic acid is a weak acid, and now we've confirmed that that's in fact true because of the available ionization of the acetic acid. Only 1.3% of that hydrogen actually ionized. Okay, so That's what it is. So it's just kind of reconfirming, but now calculating the percentage. All right. Now, we talked about this in class. Remember that Ka or Kb is pretty much the same thing as Ka, which is the concentration of the hydroxide ion, right? Times whatever that metal is, right? So in this case, that'd be the metal, and then divide it by the base. All right. So that's pretty much the same thing, except now you're working with bases. Now let's take a look at these Ka values. Okay. Let's take a look at the first one, the Ka for acetic acid, which is the same one. Where is it? Here we go. 1.8 times 10 to the negative 5, right? Ka is equal to 1.8 times 10 to the negative 5. So just like we calculate the pH by taking the negative log, right? The pKa is the same thing as saying the negative log of the Ka value of an acid, right? The pKb is the same thing, right? You take the negative log of the Kb of a base, okay? And this is what we're going to continue the next class time, all right?